for inviting me to give this talk. And Robert, I really appreciated that you are hardworking and effort to make this workshop a very successful one. Today I'm going to talk about examples associative, co-associative, and Cayley submanifolds. In this talk, I'm going to focus on the techniques we used in finding examples of Cayley submanifolds. Because similar techniques can be applied to identify associative and co-associative submanifolds. Focused on Cayley submanifolds, there are three reasons for that. First of all, Cayley geometry contains the other geometries. Associative geometry and co-associative geometry even contains the complex cases for the right dimension, C4, or spatial Lagrangians in C4. So I'm going to focus on this Cayley manifolds. So by now, I guess you already know that what are Cayley manifolds. So you actually know very well that what are Cayley manifolds, right? The Cayley manifolds are the four-dimensional submanifolds of a spin-7 manifold calibrated by the Cayley form phi. And this phi, I think Professor Blaine has described for you. The bottom line is that Cayley manifolds are volume minimizing. That's the same thing is true for associative. For example, associative will be three-dimensional submanifolds of a G2 manifold calibrated by that associative form phi. So all of this are volume minimizing. So this is because use the method of calibration. So I first would like to review for you the calibrated geometry, then review the Cayley forms, then talk about spin-7 manifolds, and then we'll talk about the Cayley manifolds in C4. Then I'm going to describe the techniques that I used to find the Cayley manifolds. And by the way, this examples found was joint work with my undergraduate students at Harvard College. And one student working on the Cayley manifolds is Chris Priss. He will be actually a graduate student this year at Berkeley. Mm-hmm. So for the similar techniques, then I'll present examples of Cayley manifolds. And the similar techniques have been applied to find spatial Lagrangian manifolds, associative manifolds, and co-associative manifolds. For example, work with on associative manifolds, I worked with undergraduate student Ian Winner. So what is the Cayley? What is calibrated geometry? And I think after Professor Blaine Lawson's talk, you already expert, right? Because the idea in calibrated geometry is very simple. So the idea is the following, that you take a manifold. Say, here's the manifold. Say this is M. So say M is equal to a manifold. Okay. So you take a differential form, phi, say phi, what is the phi? Phi is the P form. So they say this is n-dimensional, and this phi is the P form, which is P usually less than equal to n. It's just wedge K, T, stub M, you view it as a section. Right? Phi just the elements there. So what are you going to do? This phi is the calibration that phi has to be closed. Now you take this phi, try to identify volume minimizing cycles in here. So how could we do that? First, we have to identify find what is the co-mass of phi. So co-mass of phi, you already heard the Professor Rawson said. It's pretty easy. It's just the supreme of the phi. He defined the co-mass norm, which is when phi is fixed. Usually I put a star here to indicate that it's not L2 norm. It's a co-mass norm. Co-mass norm is defined to be just the supreme of all the value phi acts on cos C, such that cos C is belong to the P. It's just the P-dimensional simple vector, meaning it is decomposable. That cos C is decomposable, which is in Tm. Okay, of course, the usual L2 norm is different. As you recall, the usual L2 norm, what's the difference? The difference, we are here require cos C norm is equal to 1. Okay, here it's just the supreme of phi of cos C, for example. Cos C now is belong to wedge K T M. Wedge say K, here, let me see, sometimes I use K. So I'm talking about the P form, so in this talk, I use P form, but usually I use K. That's why, sorry for the trouble. So that's all P form here, okay? So also with cos C norm is equal to 1. So it's clearly that this one is much smaller than this one. Why? Because you are taking decomposable simple vectors. Here is general P vectors. That set is much smaller than that set. It's a very thin slice. If Tm is just a vector space, wedge P of V, say Tm is V, that is just a sphere in that vector space, which is very a lot of vectors. Here you have a little slice in that unit sphere. So that norm is much smaller. Okay. So when phi is fixed, this value is called the co-mass of phi. So this value, phi fixed, this is the co-mass of phi. Okay. So once you have this co-mass of phi, now what you are going to do? So as Professor Lawson said, you are going to really find the diamonds in the sense. You are going to looking at all the vectors such that all the P vectors, here is torus is really only two-dimensional, so the P vector, I'm drawing one-dimensional vector. So you look at the diamonds such that all these vectors satisfy that, maybe here, such that all of these vectors achieve the co-mass, meaning you're looking at the set, right? You're looking at the set G of phi, okay? Such that it's all the cos C belong to GP Tm, such that phi of cos C equal to 1. Suppose the co-mass is rescaled. You rescaled such that the phi star is equal to 1. So you're looking at the diamonds in the sense, okay, all in the all simple P vectors here. You look at those achieved the co-mass, okay? So then what is the next step in this game? It's really, okay, now you have these distributions. Let's say all these diamonds now shining. Now you form a distributions. Now you want to find the underlying space or manifold or something underlying space such that if it's integrable, it will form a cycle. If it's integrable, you form a cycle, and that cycle will be volume minimizing along in its homology class. In other words, this cycle will homologous to this one, and this with the least volume, okay? But of course, the object is not that simple, okay? So this one with the underlying spaces with the least smaller volume. But usually, underlying space could have a singularity. Things are much complicated. So we need to introduce more complicated object to which I think I don't have a time to go through the details. So like in general, you have to define current. You have to define the current, right? So in other words, where this comes from is when you look at the distribution and the the underlying space could have a singularity, could have something complicated. So you needed to generalize this classical cycle to something more complicated. So it's called P current. I don't think the name is important. The important is the idea behind. The idea behind, if you think about it, in calibrated geometry, why it works? It works is because the following key idea is that a P cycle calibrated by some differential form, it must volume minimizing in its homology class. Okay, if it's calibrated, it must be volume minimizing. You think about the proof, how this proof worked. The proof is just one line, Stokes theorem. So therefore, when you want to generalize the object to something more general, you want the Stokes theory hold. So therefore, you want to generalize this classical cycle to something the Stokes theory still hold. So first, you have to generalize the D differential operator, which is easy. Then you also wanted to generalize something can be written you can define something by integration. Okay, so that Stokes theorem may make sense later on. So the P current is really to see that you have to really define mass first. So I should have say the mass first. I should define the mass, but mass here. But if you define the mass, okay, then when you can written something integral, it's really this mass. If you define the mass by evaluate all the P forms, take the supreme of such a value, it's a mass of this U. Okay, you define the mass of U, define it like that. Okay, only when mass of U is less than infinity, it's finite, then you have a radon measure, which makes this mass of U can be written into integration. Okay, that's the key. Once you can define something under this condition can be written as integration, then you can prove in certain circumstances you can actually, the Stokes theorem is still true. I think Professor Lawson already gave you examples, which is, for example, the rectifiable current, right? So you can use everything defined to currents, which the goal, what he wanted to show you that it's actually the mass of current will come back to the volume of S if you define something by integration. Okay, so that two notion is compatible. That I don't have lots of time to get into the details here, but I want to let you know that's why where this stuff comes from. So now, there are sort of regularity results. Okay, suppose if you have a manifold, p-dimensional manifold in M, such that it is calibrated. So you wanted to see how regular it is. So the question here is, if M is originally this one, say this is originally say C infinity or C infinity, then if you find this n is C1, that n has to be C infinity. So this is a result. It's really from Maury. It's an observation from Maury's regularity theory, and famous theorem by Elmgren, and it says that if phi is the current of dimension p, phi current means it's already calibrated by phi in the language of Professor Lawson. So the support of t is actually analytic except a singular set of codimension 2. And he also explained, if, as you recall, support t minus support dt is two pieces. This piece is analytic and that piece is codimension 2. Okay, in any case. So because you know that calibrated geometry, I rather want to talk about, because all the examples you already know, so I rather want to talk about the techniques that involved in calibrated geometry, because the idea is very simple, okay? Yes, I can explain to my undergraduate students to get it right away. So the point is, when you really play the game, how hard that you can really get the result. That is the question. Okay, so how could we, first of all, the questions involved in this calibrated geometry is how to pick a calibration when M is given, or how to find the co-mass of phi, how hard is it? How to identify phi calibrated submanifolds, cycles, or currents. How to prove uniqueness aspect of results. For example, if you find all of these volume minimizing cycles, is that all? You know, or you find the one, is that unique? So this kind of result. And also you say, someone hand you, say, I solved the minimum surface system, and I got a solution, but I don't know whether it's absolute minimizing, and hand it to you. You wanted to check whether this is absolute minimizing, what you can do. So this is like in calibrated geometry, lots of questions. So let's look at some examples to see what's going on here. So for example, you already seen the Cayley manifold, okay? The Cayley manifold. Okay, so omega is the Cayley manifold. So if you say, someone hand me this manifold is Cayley, now you want to say, okay, what are volume minimizing subvarieties of this manifold? Okay, because learning volume minimizing subvarieties of this manifold really tells you the geometric structure of this manifold. So it's a very classic, important question. So once you give this manifold, naturally you want to pick a form. You say, oh, there is a calibrated geometry. You can use a differential form to find those volume minimizing subvarieties. But how? First, you have to pick up a form, right? So what is the natural thing you pick? In this case, naturally pick a Cayley form, okay? Cayley form, and you will notice it will as Professor Lawson showed that it will calibrate holomorphic curves, and wedge P over omega P has co-mass 1 by Wiqing's equality, and it will calibrate complex manifold of dimension P. So in this problem, how hard? Pick a form. It's easy, obvious, because it's a Cayley manifold, naturally pick a Cayley form. But the co-mass, I think Wiqing's inequality in here, the co-mass is hard, relatively speaking, about the other stuffs. Because in the estimate, you will, what's the game here? Okay, when you estimate something, right, you get, say, phi, estimate some plane, say P, okay, decomposable simple plane, okay? Then you estimate the norm here, okay, the norm here. Okay, then you norm. So what happened is you calibrate then you do this, like evaluate this one, yes, absolute value, you calculate the absolute value, so you less something, less something, less something. More or less equalities, say particularly the value is 1. More equalities, every estimate has to be sharp. The equality has to be hold at some time. You don't want it too big. So more equalities tell you one holds has to be this holds, this holds, this holds. And more equalities tells you how tangentially, how this tangent plane, this calibrated plane, the structure, how kind of structure, more structures. Therefore, the down space, it's easier for you to, a little easier, from my experience, a little easier to figure out. Okay, while if you calibrate, say in our spatial Lagrangian case, you have 2 steps, it's already less equal to 1. Equality easily holds. Then the tangent plane just have little structures. Then the underlying manifold have a lot of choices. Then to find the manifolds become harder. Okay, so like so it could be, if you find the co-mass is easier, this piece become very, very hard. If find the co-mass is very, very hard, this piece become a little easier. That's from my experience. For example, so in Calabi-Yau case, I already covered it, which is like a spatial Lagrangian case, because you already seen this, so I'm not going to go through the details. So for example, in Grassmann manifolds, okay, find the co-mass actually is very, very hard. Okay, so for in G2R4, like G2Rn, which is still the first Pontryagin form. So for example, Grassmann manifold, now you say determine the geometry, volume minimizing subvarieties of Grassmann manifolds. You naturally to say well, which form I'm going to, differential form I'm going to pick. Of course, the characteristic forms, right? So it's a Pontryagin classes or Pontryagin forms. In complex Grassmann manifold, you definitely pick up 10 forms, right? So the point is, in the G2Rn, the P1 it's a multiple of omega, which is the Cayley form. So the co-mass is 1. This piece is done. But the bigger Grassmann manifold, all this co-mass, it's very, very hard to figure it out. Okay, but once you figure it out, you have so many equalities it has to hold. Therefore, this calibrated plane have lots of structures. So to figure out what is the manifold underlying, it's a little easier, but it's still not that easier. For example, say in G3R6, as G3R6, this is the volume minimizing cycle. But where this comes from, as you recall that the topology of Grassmann manifold for GKRn, the Beatty number achieves the largest value at G4R8, which is Beatty number is 3. Then immediately stabilized to 1. Okay, it's always 1. That 1, that generator, okay, it's come from G2R4. G2R4 is the only reducible Grassmann manifold, meaning can be written 2 pieces. That piece is when you embed it to here, in here, this piece is volume minimizing. But embedded here, that class is not, in this class, when you come into here, it's no longer volume minimizing. In that class, this one is homologous to this one. The suspension of RP3, which is 3 necklaces like this is have a less volume than that. You notice you have a singularities. Okay, when this one embedded to G4R8, this piece is no longer volume minimizing. Okay, in the same homology class, the S4 actually is volume minimizing. Okay, but how to find this one, for example? This is not that easy. Okay, but people can guess. This is actually a generator, a corresponding homotopy class, and they guessed that this might be calibrated by first Pontryagin form, and they evaluated it does achieve the co-mass everywhere, the tangent plane. Okay. So if you want to see details, I just, because this notes they said needed to give to you, so you can see the details that for this Grassmann manifold example. I just want to let you know that how hard when you sort of dealing with this calibrated geometry questions. So another thing is you also can say how to prove the uniqueness. As I said, for example, in here, if that this kind of S4 or something else could be volume minimizing in here, calibrated by first Pontryagin form. So there is a way you can actually do it by. Theoretically, there is a way systematically doing this one. I think our experts is right here, Professor Robert Brown is right here. So you really can actually sort of like lift the system, for example. You can, I say how to prove certain uniqueness result. It also can use it to find cycles, but sort of you have to have some feelings, because once you get these systems and differential equations, if you don't have any guess, it's very hard for you to tell globally what it is. So it would be nice. You already have some guess, so you have to be very familiar with these generators of cohomology or homotopy generators, whatever. You already have some idea. Then you look at the system, sort of 2 ways. So make it really come out. But this is very powerful for prove uniqueness result. For example, we proved that S4 actually, in certain sense, up to isometry, it's actually unique. We really, by associating a family of calibrated plane, a fiving system to symmetrical group SOKN. In other words, here Grassmann manifold is written homogeneous SOK, GKRN written as SOK plus N over SOK cross SON. So I lifted the system on the top. And this is actually the work with Dan Grossman. So we can prove that you actually yield uniqueness result. But use this method, as Mariarty was talking about, also use this method case by case, got lots of known examples and also some interesting other results. So this is also a way to do it. But I would think it would be interesting. You already have some guess. That's much, much better. OK. So another question is that say someone give you a minimum manifold. They think that they guessed, they guessed that this piece is minimal. It's supposed to be volume minimizing. So what you do? So for example, right? In 1996, Lawson and Osman actually discovered a very interesting four-dimensional minimum surface, which is not C1, by solving a non-parametric minimum surface system. So as you see in his talk, it is a cone on the graph of a Hopf map. It is a cone of a Hopf map. Okay, so consider a Hopf map from S3 to S2, then map Q to Orbivez map, and define the cone by usually you always can define cone Q norm HQ over Q norm, and you calculate it out is this result. So it's a cone over there. But they don't know. This is just a mean curvature system, the critical points of mean curvature flow. So you got a solution, but they don't know whether this is absolutely minimizing. Okay? But this is defined by quaternion number. It's four-dimensional. So naturally, they guess it's calibrated by co-associative. And they checked it is. So actually, this one is volume minimizing because. So you can, in this case, the important issue here is to pick which form become essential. Okay, so the problem changes from time to time. Okay. Oh, that is, you're right. Thank you. 1976. Sorry, it is 1976. Thank you. Okay, I'm sorry. So, in any case, so there is also how to find this calibrated submanifold and the cycle. It's usually, most usual method is write this everything down, okay? Then you make it a PDE, solve the PDE. That's really the basic bread and butter. It's there. The point is you can't solve the PDE. That's the point. That's the trouble. But that's the calibrated geometry. I think that's what I wanted to say. Now, I switched the gear. I want to talk about, next one is talk about our example, which is Cayley calibrate the manifold. So what is the Cayley form? Cayley form, you already know. The Cayley form is just, in the one of the tangent space, locally it's just the phi xy zw is x inner product with y cross z cross w. And the cross product you already know. So this I don't think I need to say a lot. All I want to say, this phi is closed alternating and has comass 1. So you already familiar with the normed algebra, how to get this Cayley number by Cayley-Dickson process. And you also know what is the cross product, which is like x cross y cross z. It's really x, y, z, x, y, z. The bar is all in the middle, the associated. It's just backwards. Okay, x, y is half of it. And it satisfies all these properties. And I bet you already know that if you want to satisfy certain properties like that, and say, example, this one, this property, and this kind of perpendicular property, they are only cross product only exists after 3. Okay, this you already know. So the differential phi, okay, form phi is, maybe I should talk about this one a little later. Okay, this phi also can be decomposed to two pieces. Okay, and also can be written local coordinates like that. So this E1 can pull out. So therefore, you have one wedge phi plus staff phi. Okay, this piece is co-associative and that piece is associative. So in this sense, you will see later in a few minutes that the calibrated geometry, the Cayley geometry, contains the other geometry, associative geometry, co-associative geometry, complex surface, and special Lagrangian. Okay. So the spin 7 manifold. So what are spin 7 manifold? A manifold is called a spin 7 if its holonomy is contained in spin 7. So in this talk, we have, in this talk, like R8, T8. In this talk, I'm going to focus on R8, but R8, T8, and Joyce's example, T8 over this finite group of automorphisms of T8, and which preserve the spin 7 structure. And he got this example by blow up the singularity, resolve the singularity, get the new examples here. So that is basically known examples. But there are many different ways to describe a spin 7. I'm going to take Professor Robert Brown's definition, which is preserve the form. Probably you know that the spin 7 is sort of preserves the G1xy equal to G1xg2y, or this one called Cartan triarity. Just like G2 is the automorphism group of the autonia. Or you can think spin 7 is subgroup generated by unit quaternion imaginary numbers by right quaternion multiplication. That, I think, Professor Lawson talked. Okay? So I'm going to use this one. Or you probably know that spin 7 is double cover of SO7. That's also a way to define spin 7 manifolds. Okay. So why spin 7? Okay, spin 7 acts on a set of calibrated Cayley planes. Okay, it's transitively with isotropy subgroup. It's SU2 cross SU2 cross SU2 over Z2. So the homogeneous space G5 can be written as spin 7 over K because it can be written so it's actually homogeneous. So what happened is how we define the action there to see that. So like if you have a set of octonion number written as two copies of quaternion number, A plus BE, then if you map over, so you have a 3 number, Q1, Q2, Q3, so you act as Q1, Q3 bar, Q2, Q1 bar. And you can see if, for example, Q1, Q2, Q3 all equal, this represents a rotation here. It's SO3, here's SO3, it's a double curve SO3, so that makes sense to you. Okay, so you already know the Cayley manifolds. Cayley manifolds is just all the tangent planes are Cayley planes. Okay? So Cayley manifolds, as I said, contains several other geometries. For example, okay, a submanifold M, which lies only in imaginary of O, then it is Cayley if and only if M is co-associative, because you can look at this one, right? Staff phi. If this piece is 0, okay, this piece even acts on it or 0. So this piece, I really should go here. If this piece equal to 0, phi acts on cos equal to 1 means staff phi acts on cos equal to 1. So it's co-associative plane. So that's what happened. Another thing is I should put there. look at. Okay. A submanifold M of a form R cross N, okay, is Cayley if and only if N is associative. That's also the same reason. This piece is 0, and 1 star cross phi. This phi actually will achieve 1. Okay, that's the same thing. Then next, if you have this is, I think Professor Lawson talked about it. If you fix a unitary imaginary quaternion, consider complex structure GAU on this one, then the complex surface in O with the reversed orientation will be a Cayley manifold. It's really because this decomposition, the reverse orientation, because the negative sign here. Okay. So then you also can look at say this piece is 0, and this piece is 0 really tells it's Lagrangian, and this one tends to 1 becomes spatial Lagrangian. Okay, so if the dimension is right, it's in C4, then each spatial Lagrangian submanifold is actually Cayley manifold. But we are interested in find examples which is not this type. Okay, I call this type, call them trivial Cayley manifolds. It's not that trivial, but what I want to find is not this type of example. Okay, so next. I did not switch all the transparencies there because some transparencies you already know the stuff, so I don't think it's worth to put there. So, question is why Cayley manifolds are interesting. So, you know in 1996, that's in 1996, okay? In SYZ paper, they talked about why spatial Lagrangian is important in Miller symmetry. So later, okay, there has been new interesting in geometry of Cayley cycles. Following SYZ, the roles of exceptional geometry in Miller symmetry were first investigated, the so-called Baker-Morrison. They call Baker-Baker from Caltech. And all of those people, they investigated spatial interesting in Cayley cycles. So from physics point of view, they showed that Cayley cycles in spin 7 holonomy 8 manifold, it's preserved half of the space-time symmetry. But if you view that the holonomy is small, it's in Calabi-Yau, it will only preserve a quarter of it. So from physics point of view, this cycles really represents some different objects there. Okay, so they conjectured also, you know, what kind of roles that Cayley cycle will play in Miller symmetry. Okay, for Calabi-Yau for folds. So in 3 folds, sort of like a complex S1 or R cross a holomorphic curve, holomorphic stuff corresponding to the spatial Lagrangian. And but in 4-dimensional, they guess Cayley manifolds and Cayley manifolds corresponding each other. So there is a certain cohomology class, which is you need such a Cayley cycles to fill that spatial cohomology class there. So they do need such an example, and they propose to find explicit examples of Cayley cycle to demonstrate their conjectured phenomena. But in fact, when Professor Edward Whedon came to California once, he was talking about, I think it's in San Diego, he talked about his M theory, and in his talk, he talked about find a BPS state, which is actually, I noticed actually really he means calibrated cycle. Okay, so, but he was talking about actually associative cycle. So what he want? He said in his talk, you have M theory, and then all of this, like on the limited cases, that would be 5 different string theory. So he interested to find cycles like this type. So he wants to find something like in the middle. It's associative. Associative. In the middle, it's associative. But somehow, asymptotically, it will be, say, S1 cross some special Lagrangian cycle. Okay, so somehow here is his M theory. Here is his M theory, but asymptotically it becomes the string theory, which is special Lagrangian cycles. So, or he wants some kind of a family of associative cycles approach to a cone, or something like that, so that the cone side still has this special Lagrangian piece there. Okay, I actually, after his talk, I said, is this BPS, would you say, saturated inequality look like it's just a calibrated cycle? He says, yes, it's actually associative cycle. So he wants something in the middle is in his M series, really the associative cycle. When you go to the limit case, it becomes special Lagrangian cycle. That's what he wanted. Okay, so, but then you would ask why this Cayley manifolds is important. Cayley manifolds, there is F theory, similar story. Okay, so you need to find the Cayley manifolds. Here's Cayley asymptotically becomes something cross-associative. Okay, so you want the asymptotically become something they wanted. That's what I understand. Okay. So, or you want to find a family of them approach to associative cone. It's Cayley manifold, but in some cases approach they don't want the result here associative example exists. You can use mean curvature flow. Say start as with Lagrangian. You can prove for us mathematicians, very important. You know, you can follow mean curvature flow. Then you say, okay, you find the energy function, whatever the function, mean curvature function, whatever, and then you find the critical points. You say, okay, we find a special Lagrangian. They want concrete example so that they can write the metric using that example. Okay, so they really wanted something you can write it down specifically. Okay, so then from that point of view, I thought, well, the best way is go through the PDE. Okay, so we went to the PDE of the Cayley manifolds. As you see that Professor Lawson said, in the associative cycle, something like this, but co-associative cycle, you have a tutor, and the Cayley cycle, you have a pseudo operator. But in general, this is equal to 0 always true. So what are these? Let me recall for you. Those are, that equation is important, put it here. Okay, so the direct operator D is, we just see previous talk, okay, in all special cases, this one, and the first order Mongeon-Ampere operator is defined this cross. Each of F is a vector here, okay? Partial F, partial X2, it's a vector. F, partial F1, partial X2, partial F2, partial X2, right? It's F is F1, F2, F3 here, okay? So you cross product them. You write it out. That would be very, very complicated. Actually, I wrote it out. It's like you take the Jacobi, okay? Partial F1, partial X1. You take the Jacobi. It's a 4x4 Jacobi. It's like you look at the main minor, okay? It's the chairs of adjoint of this one equal to chairs of that matrix. It's 4 of them. So if this vector F viewed as gradient of some function, that this becomes second order. Therefore, they call Mongeon-Ampere operator here. Okay, so it is a system Mongeon-Ampere operator equal to a direct operator. Okay, so it's very hard to solve. You know, no one actually knows how to completely solve them. Even I asked Professor Yao, he told me, he says, well, I solved the Calabi-Yao conjecture, you know, it's reduced to become a PDE, really solved this one. Now it's a system full of them. This is a complex Mongeon-Ampere. So it's all very, very difficult. So So what we can do, following their idea, what they wanted, so we think we can sort of find Cayley manifolds by adding certain symmetry to candidate cycle. Okay, so suppose I have, because the PD is too hard to solve, so I take an arbitrary curve, then I sort of use subgroups of spin 7, okay, act on it and, make it come out with, why I use subspaces of spin 7. In other words, if this tangent plane is Cayley, okay, under the spin 7, if a G is contained in spin 7, right? So the form, you remember, spin 7 is all the elements in SO8 that preserve the form, meaning if this is a Cayley plane, under the subgroup, the orbit of it, this bring here, it's still Cayley. This is still Cayley. You see what I mean? All the Cayley planes. So I all needed to, restrict put symmetry restrictions to the PDE to make the PDE become simpler. That's the idea. Okay. So that's the idea. So then we classified all possible three-dimensional subgroups of the SP1 cross SP1 cross SP1, which is not hard in this case. So there are lots of them, but you can show there is you can like all this subgroup. You can here say I could fix the P inverse Q P inverse or something. You have a lot of finite subgroup combined with this. It's all still three-dimensional, okay? But you will notice actually you can reduce the other cases, you can reduce to this three case. Others you can algebraically play the game so that it's reduced to these three cases. For finite subgroup, you're adding more restrictions. So if you solve these cases, then finite more restriction onto it, you just get a subfamily of it. So actually we reduced all of this. For example, if you take this Q1Q, okay, what does this mean? That means like if this is Q1, Q2, Q3, the action is Q3A, Q1 bar, Q2, B, Q1 bar. This is really means that action. Okay, so here, like if you take this Q1Q, okay, you find the subgroups. It will contain co-associative cycle that Professor Blaine given. Okay, it will get a family, but one of them is co-associative cycle. Just when you solve the PDE restrictive imaginary part, you will get his example. But we consider all the subgroups and we just going to solve the PDE. But in this case, because the group is just generated in one variable, okay, here. So your PDE can further generate it, say, under this action, this equal to 0, if and only if this can take it away because the PDE have also certain symmetry. Okay, so that reduced our job a little bit. So we actually use this method. We find examples such as, this is the two most interesting examples we find. There are some other examples, but I think these two mostly. One is this one, okay, Sx over X norm, Xe. Here, this X and S set implicitly defined like this one, okay. They are actually, you can check, it's complete. We're interested in complete examples. Locally, lots of examples, okay. And this example also is complete. It's defined like this one. It's a family of it. For example, C changes, okay. This family depends on CKS, okay. They are family of them. That's what we wanted, okay. Like this one, when C tends to 0, it tends to cone. Okay, so that's interesting. I think in associative cycle we also get something like that, and the physicists really interested. Okay, so let me show you some pictures here. Like I actually have the colored ones, but this machine does not make a colored copy, so I just simply copy from our paper. For example, the first example you see is you look at the slice. Say, because it's 4-dimensional, I only can look at the slice of Cayley manifold in x3, x4 equal to 0, you get this one. And if in EJE, my basis is 1IJK, IJEK, okay, EIJK. So you will get a slice like this one. And in here, you get the slices. This one, we actually made the animation. It can change from, you can see how it changes, okay? And when also the C changes, this one will shrink to a cone, the family. We're here is particular choosing, I think, particular C is 5 or some kinds of number, which made the picture. It's just one member of this Cayley manifold. This is the slice of that member. Okay. So like in second example, okay, this is also implicitly defined, and it has several actually branches there. This one here, it has several branches. Okay, one branch here, one branch, several branches there. Okay. So, but it is still complete. It goes infinity. Okay. And also, so as I said that each member we check that it's actually complete. In certain cases, they present certain kinds of cone, and we do have a family of Cayley manifolds approach to cone. That's what they wanted. And in the case of cone, you can see the solution to our Cayley equation is not C1, because if it is C1, we just had regularity theory. It has to be smooth. Okay, so it is not. Okay, in any case, it's actually Lipschitz. So what we did, we classified, as I said, all the subgroups of dimension 3 in K, and we used each subgroup as an action, add a symmetry restriction to the PDE, and simplify the PDE. Then we solve them, and then we prove the uniqueness for obtained list in our paper. So let me just give you a little bit idea how it will. For example, you restrict to for example, the last case. I think this action is QQQ action. And once you have this QQ action, then you want this F from H to Y. We choose the subgroup in the isotropic subgroup, because you are talking about the graph. You want this being fixed, and then this being fixed, and the orthogonal complement automatically fixed. You want it fixed. So we look at the subgroup there. And then, for example, if you put the symmetries onto it, you find these candidates here, then the F, the graph function, has to be x phi of something. In other words, this function will reduce to 2 variables. What is really matters is the real part of x or the imaginary norm parts of x. It has to be satisfy x phi plus another new function, where phi and nu both real functions. And in this case, this is the candidate, so you really need to determine what is phi and nu look like. Then you plug in the PDE, and I call this piece is R, this piece is S. Then you get all these PDEs here. And then this is still not easy to solve. We solved, say, this equal to 0, this equal to, plug in solved. Then we proved that there's no other solutions. Actually, to prove there's no other solutions with more than 10 pages. But to solve case by case, certain cases you still have to prove up to last point. There's no other solutions. Okay, so this is, you get an idea what's going on. So now, this is a Cayley cycles. So similar techniques used to find spatial Lagrangian manifold and associative manifolds. Spatial Lagrangian, I find many of them, it's already known, to be honest. But the associative manifolds, we have interesting examples. Okay, so But in this case, when we solved it, you only can, if you consider like a G2, like let's recall, G2 is just automorphism of octonial number, and G2, Robert Bryan's definition is preserve this associative form, and the isotropic subgroup in this case, G2 acts transitively, isotropic is SO4. So similarly, we look at the subgroup of SO4. If you look at the two-dimensional subgroup, it's too much restrictions. If you get candidates plug in, you just does not get interesting examples. Okay, so we have to consider one-dimensional subgroup here. But then plug in the PDE, you don't get ODE, you get PDE majorly. Okay, so in Cayley case, sometimes get ODE, sometimes get PDE, but majorly it's ODE. Here is majorly get PDE. Okay, so we get some interesting examples, and we also proved the uniqueness recently, and now the last thing we'll talk about. I don't have time to talk about. So working in progress, and we originally this problem was proposed by Professor Gang Tian. He asked me to find Cayley cycles in T8. We did this in linear case. Linear case, we solved it. It's interesting. If you have ladders, it closed it up, and also has to be Cayley. It will be related to like a what do you call like in the number will be related to right triangular number integers. So say 3, 4, 5. It's a solution to. I mean the other way around, of course. 3, 4, 5. It will be related to these integers, all these series. Okay, but in linear cases, and we also interested to have a systematic way to construct the Cayley cycles. One of the students interested look at it, or the finite subgroups in spin 7, and I think he already classified. But also we were thinking about, because in their content, people interested to look at, say this is a spin 7 manifold, and the boundary says G2. And you can look at all these Cayley cycles. Cayley cycles lies inside, such that the boundary lies in G2. Then this piece here is associative. So you look at the moduli space of this one, such that you want the condition such that when asymptotically this become sort of this type. But I don't have the time to go through. So this is what we are looking for. And we also, this summer, we also worked on regularizing singularities. For example, if you have a pair of cone, if you get a cone, you want to resolve this singularity. So what we did is we were thinking about, I think we actually first thought we solved it, but we find that over one parameter subfamily group of family have some trouble, so we could not state the results. But the point is, you can remove the singularity by doing connect the sum. For example, if you have M1, M2, it's Cayley manifold of compact spin 7 manifold, and the intersect transversely at a single point. And the union can be thought of as Cayley manifold with a single isolated singularity. So we wanted to regularize this one in certain sense. But in other words, we hope find a family of spin structure. You have to change the structure, XY on X, and a family of Cayley manifolds, XY on XY. In other words, you want to change it so that MI phi will tend to this singular piece. The spin structure also tends to this one. Okay, we don't know whether you can actually fix this spin without changing this spin structure. We don't know. But it seems to work for the complex torus and in this condition. But somehow we rechecked our calculation. We find one family of parameter, you need a deformation operator depend on one parameter subgroup. We thought this one in spin 7, but we finally find something's wrong there. So that's all. But it seems to work. We are fixing it. That's the trouble. But in any case, that need to add a roller neck. In other words, you take the singularity away, you add a roller neck. Okay. But anyway, I stop here.
So in particular, that last remark you made about Lawler nets, so it's the same idea as was used in the special